So there we are. The dot product. So the dot product of two vectors u and v is defined as u dot v equals u1 u2 u1 v1 plus u2 v2 plus u3 v3, where u is equal to u1 u2 u3 and v is equal to v1 v2 v3. So if you have two vectors, each with 3 coordinates, then the dot product of the two vectors is equal to the sum of the products of the coordinates. Of course, if u is just 2 coordinates, u1, u2, and v is v1, v2, then u dot v is u1, v1 plus u2, v2. So if you have many coordinates, then you just add the product of likewise components, all right? And that's what you call the dot product. Example, if you have u equals -1, 3, v equals 2 and 1, then u dot v is nothing but -1 times 2 plus 3 times 1, which is -2 plus 3 equals 1. So the dot product is a number. It's not a vector. When you do the dot product of two vectors, what you get is a number. So alternatively, u dot v is nothing but magnitude of u times magnitude of v times the cosine of theta, where theta is the angle between u and v. So if you can measure the angle between u and v, then u dot v can also be obtained as the product of magnitudes of the two vectors times the cosine of the angle that is between the two vectors. Or let's say we can say two vectors u and v are such that magnitude of u equals 2, magnitude of v equals 3, and theta, let's say it's pi over 3. So the angle between the two vectors is pi over 3, the magnitude of u is 2, the magnitude of v is 3, then u dot v is equal to magnitude of u times magnitude of v times cosine theta, which is 2 times 3 cosine pi over 3. And the cosine of pi over 3 is 1/2. 1/2 times 2 times 3, that's 3. So the dot product in this case is equal to 3. So you don't always need to know the components to be able to get the dot product. Sometimes you might have the magnitudes of the vectors and the angle between them, and that helps you find the dot product. Sometimes you will have the components of the vector. If you have the components, as in this case, you get the dot products by adding the products of likewise components. We have any questions? Now, properties. Two vectors are orthogonal if and only if the cosine of theta is 0. So if and only if the angle between the two vectors has cosine 0, in other words, u dot v equals 0. So two vectors are orthogonal. Orthogonal means that the angle between the two is 90 degrees for pi over 2. So the two vectors are orthogonal if and only if the angle between them is pi over 2, and so the cosine is 0, or else, in other words, u dot v is equal to 0. Example, you could say show that u equals 1 minus 1 and v equals 1, say 2, 2, vector 2, 2 are orthogonal. If we want to show that these two vectors are orthogonal, the answer would be u dot v equals 1 minus 1 dot 2, 2, which is 2 minus 2 equals 0. So the dot product is 0. That implies that the two vectors are orthogonal. Any questions? Mhm. Now, there's no question. Let's move on. Orthogonal projection. So we have a vector u here. And then we put a vector v. We want to find the vector projection of u onto v, which means go to the endpoint of the u arrow, draw orthogonally to the vector u, make an angle pi over 2 there, and then what we call the vector projection of u onto v is this. You want to figure out what this vector is. Okay. Now let's say we take the angle here, theta, which is the angle between u and v. And let's say we call this scale u and v. And what I call the scale u on v is the scalar length of this vector. We know it's a vector that is in the direction or opposite to the direction of v, and we need a magnitude of it, which we call here the scalar projection of u onto v. If I take the angle here, knowing that this is a right angle, what would be the relationship between this vector, this one, and the angle here? Anyone wants to try? Want to say something, Nicholas?
Would it be that the scalar vector that you're trying to find would be the cosine of that?
You do have the right idea. You need to start by the cosine. So cosine of theta is equal to what?
The vector you're trying to find over u.
Divided by, not u, but the magnitude of u, right? So which leads to say this. Magnitude of v cosine theta, right? Do we agree?
Yeah.
All right, now that's the first step. On the other side, we just said that cosine theta, how is it defined?
It's defined as the scalar over the magnitude of u.
No. Don't look at that. Prior to this, I gave a definition of cosine. The cosine of the angle between two vectors. How is it found?
It's the horizontal component over the magnitude of the hypotenuse, one that's acting as the hypotenuse.
No. That's the first part. The first part you just had of this lecture. U dot V is defined as what? The alternative definition. We defined the second, we gave the second definition of U dot V as magnitude of U times magnitude of V times cosine of theta. So cosine of theta is U dot V divided by the product of the magnitudes. So that's what technically here is going to be used. So cosine of theta is U dot V divided by magnitude of U times magnitude of V. That's from the definition that we got on the previous page. Now you have that the scalar projection is that, and the cosine can be found using this formula from the previous notes, and that leads to say that the scalar projection of the vector u onto v is equal, when you multiply cosine by the magnitude of v, the magnitude cancels. So you get u dot v over magnitude of U. So that's how you find the scalar projection of a vector U onto a vector V.
Dr. Long, I have a question.
Sorry, there is a problem here. This is magnitude of U, right?
Yeah, that's what I was going to ask about.
Okay. So this is magnitude of U. And right here, when you multiply by magnitude of U, you remain with magnitude of V in the bottom, right? That was worrying me already. So this is U, magnitude of U, and that's magnitude of V, because when you multiply, the magnitude of U cancels, you remain with magnitude of V there. All right. So now to go from the scalar projection to the vector projection, we need to multiply the scalar projection by the unit vector of the direction V. So we say the unit vector of the direction V is V divided by magnitude of V. I gave you this last time. This being the unit vector, that implies that the vector projection of the U onto V is equal to the scalar projection of U onto V times that unit vector, which is V over the magnitude of V. Therefore, you can find that the projection of the vector U onto the vector V equals, and that's U dot V, and then magnitude of V times magnitude of V is nothing but V dot V, and then that is times the vector V. So that's the formula that you can use to find the vector projection. Notice that V dot V is a number. U dot V is a number. V dot V is a number. So all this here is a number to rescale the vector V, which makes sense because we say we are finding a vector projection onto V. So the vector, this vector that we are finding, must be a vector that is supported by V. And it's indeed that vector that is on the line with direction V. So when you are asked to find the vector projection, you need to know that your final answer is a vector. It's a vector that you're finding. A vector that is supported by V. A vector supported by V. Questions? Example, we get U equals 1, 2, V equals -1, 3, and then scalar projection. You would say the scalar projection of U onto V is equal to u dot v over the magnitude of v. So the scalar projection of u onto v equals, and this is scalar, that's a number, that's what it means. U dot v, it's 1, 2 dot minus 1, 3 over magnitude of v, which is square root of negative 1 squared plus 3 squared. And this is equal 1 times minus 1, 2 times 3 plus 6 over square root of 10. So the answer is 5 over square root of 10. That's the scalar projection of u onto v. And now let's say I can actually find the scalar projection of v onto u. So if I want instead to project v onto u, that's going to be u dot v over the magnitude of u. So it's always over the magnitude of the one that you're projecting on. So if I'm projecting v on u, I'm going to divide by the magnitude of u. And the u dot v doesn't change. U dot v is still 5. And the magnitude of u is square root of 1 plus 4, which is 5 over square root of 5. That's root 5. So the scalar projection of v onto u is root 5. And the scalar projection of u onto v is 5 over root 10. Now, what if we want to find the vector projection? So we say projection of u onto v. That's going to be u dot v over v dot v times v. And that is u dot v is 5 over v dot v. It's the magnitude of v squared. V dot v is 10 times v, and v is negative 1, 3. That's it. And so this is 1/2 negative 1, 3, which is nothing but negative 1/2, 3/2. So this is the vector projection of u onto v. Questions?
So for the dot products on the bottom, you can just multiply the magnitude to it for that instead of having to go through the whole coordinate process.
Can you say that again?
So for the dot product of b times v on the bottom there, you multiply the magnitudes. So can we multiply the magnitudes instead of the coordinates just all the time, or no?
It's always the magnitudes. That's u, that's v dot v. And what you need to know is right here, v dot v is the magnitude of v squared. Because the magnitude of v is the square root of sum of squares. Does that make sense?
Yeah.
So either way, you're going to get the same result. Whether you multiply the magnitudes or you do the dot product of the two vectors, you're going to get the same thing. Other questions? Is there any other question? So everybody understands this. All right, example that you guys can do for me. Exercise. U equals 1, 2 minus 1, v equals 0, 1 minus 1. Now you got to find the scalar projection of u onto v and the vector projection of u onto v. Take 5 minutes for that. What's the answer?
I can give mine.
All right. What's the scalar projection of u1 to v that you find?
So I use the equation u dot v over the magnitude of v equals a scalar. And so it was the vector, the dot product of the coordinates 1, 2, and then -1 times the dot product of 0, 1, and -1, and then over root 0 squared plus 1 squared plus -1 squared. So then from that, I got on the numerator 0 plus 2 plus 1 over root 2.
Right.
And it came out to 3 root 2.
That's right. So you get 3 over root 2 as answer. And now for the vector projection, what you get?
So for that one, I use the equation u dot v over v dot v times the vector v. And so I plugged in the numbers for that. So we already knew that the magnitude of, or not the magnitude, but the dot product of u dot v was 3. So I had that on there. And then the magnitude of v was root 2. And then so I squared that and got 2. And then multiplying that by the coordinates 0, 1, and -1, I got 0, 3 halves, and then -3 halves is the final answer.
That's correct. So that's it. That's how it's done. Just as simple as that. Any questions? All right. Let's even before we get here, let's do first the cross product. So if you have u equals u1, u2, and u3, and I recommend to put v right under it, v1, v2, and v3, we define the cross product u cross v as the vector that is defined as follows. For the first component of the vector, you cover the first column here and you report the matrix that you see. So that is u2, v2, u3, v3. For the second, you cover the second column and you report the matrix that you see with a minus sign first. So you have a minus sign, then u1, v1, u3, v3. And the third, you cover the third column and you report the matrix you see, u1, v1, u2, v2. That's it. That's how you find the cross product of two vectors. And that vector that you get is a third vector. The main property of that vector is that u cross v is orthogonal to u, and u cross v is orthogonal to v. So u cross v is a vector that makes an angle of 90 degrees with both u and v, with each of them. And you can prove that by easily doing u cross v dot any of the two, you get 0. All right. Example, if you take u equals 1, 2, 1, and v equals 2, 0, -1. Then you have u cross v equals, like I said, cover the first column, you get 2, 0, 1, -1. Put a minus sign, cover the second, 1, 2, 1, -1. Cover the third column and report what you see, 1, 2, 2, 0. And you must follow that order. And now this is equal. Each of these is a determinant. How do you compute a determinant? You do this times that minus this times that. So this is 2 times -1. It's -2 minus 0. So that's -2. Then you have a minus sign, and then you get -1 minus 2. Minus 3 times minus, it gives you 3. Then 1 times 0, 0, -4. So it's -4. So that's the answer. That's U cross V. And now you can check what I just said, that U cross V is a vector that is orthogonal to U and is orthogonal to V. So let's say here, U cross V, take it as a vector and dot product with U. What are you going to get? So you're going to get -2, 3, -4, dot product with 1, 2, 1. What is it? It's going to be -2 times 1, that's -2, plus 3 times 2, 6, plus 6, minus 4 times 1, -4. And you can see this is 0, right? As expected. I told you U cross V is orthogonal to U, which means if you do the dot product, you're going to get 0. Okay? Any questions? And you can do the same thing for U cross V dot V. You get 0 as well. Is there any question? Okay. Exercise. So we got U equals -1 to 0, and V is -2, 0, 3. Question: find U cross V, B. Show that U cross V is orthogonal to V. 2 minutes for that. Can I have the answer, Eric?
Yes.
So what's your answer here?
Well, you got to do the vector, and then it's absolute sign, and then it's 2, 2, 0, and then it's 0, 3, 0, 3.
Yep.
And then minus absolute sign, -1, and then -2, and then 0, and then 3.
Yep.
And then it's -1, -2, and then 2, 0.
All right. And then
I got 6,
yes.
comma 3,
Yep.
-4.
There's a minus here. This minus that.
4.
4. So that's a cross product. And now for part B, you need to do U cross V dot V, which is 6, 3, 4 dot -2, 0, 3. And that gives you 6 times 2, 6 times -2, -12, plus 0, plus 12, and that is 0, which shows that the two vectors are orthogonal. Notice that if you get the wrong answer in part A, you certainly find out that this dot product is not 0, so you will understand that you have a mistake. All right, that's it for this one. Now, the third part and fourth part of this lecture is about points. So vectors, points that are on the same line. Or we say collinear. So if you have 3 points that are on the same line, then what will happen is if you have A, B, C that are points, and you want to check if these 3 points are on the same line, what you need to do is to form the vectors, form 2 vectors, AB, AC, for example. Could form any 2 vectors, AB, AC, for example. So, and if you form those vectors and you find out that AC cross product with AB is equal to the vector 0, then that means that the 3 points are on the same line. That's if and only if A, B, C are on the same line. Okay? So if you want to show that 3 points A, B, and C are on the same line, what you need to do is form the vector AC, form the vector AB, and do the cross product. If you get the vector 0, then you conclude that they are on the same line. If it's not the vector 0, then the 3 points are not on the same line. And notice that cross product here means you need to have 3 components to use that formula, right? So if you do have points that are given to you in 2 dimensions, then you can add the third components as 0 before you do this. Otherwise, you can't have a cross product, right? Am I making sense? And then I'll show you here something else that can allow you to understand why this is true also. And which gives you also another problem that you can have with vectors. So, say 5 here. Area of rectangle, triangle, and parallelogram, any parallelogram. So let's say we have these points, that's A, B. Let's say we have C here and D there, and then we can close here. Let's say this is the vector AD. Let's say this is U, and that is the vector V. Okay? Just tell me, what do you remember from your high school program? How do I find the area of this thing if I know the length here and I know the length here and I know this height? How do I find the area? If I call this H, how do I find the area of ABCD? Anyone remembers? Is there anyone who can say anything now? So the area is it not magnitude of U times H? Huh? That's what it is. Okay. And H, if we have the angle here between U and V, you would say that H equals to magnitude of V times sine theta. So that area is magnitude of U, magnitude of V times the sine of the angle between these two. And this thing here is the magnitude of U cross V. So if I want to find the area of the parallelogram, based on U and V, or with sides U, V, and it's equal to the magnitude of U cross V. And that is the reason why when A, B, and C are on the same line, that means that these two lines, BC and BD, are same, so they collapse. There is no area between them. The area is 0, so the 3 points are on the same line, even only if that cross product is 0, because it makes the area 0. That's why this. Am I making sense? So when you take 3 points that are on the same line, A, B, C, then the line BC and the line AD are same. So the area is 0, which is because the cross product is 0. And so this is the formula you would use anytime I want you to give me the area of a parallelogram that is based on the vectors U and V, or with sides UV. And the area of a triangle ABC will therefore be 1/2 of the magnitude of AB is AC. Why 1/2? Because the triangle is half of the parallelogram. Questions? All right, example. So we have these 3 points, A, B, and C. And the first question, are A, B, and C on the same line? Or Colin, are A, B, C on the same line? So answer, form the vector AB. How do we form the vector AB? Take coordinates of B minus coordinates of A. So that's 1 minus 2 minus 1, 1 minus 1, 0, 1 minus 0, 1. Form the vector AC. Take coordinates of C minus coordinates of A. Minus 1 minus 2, minus 3. 1 minus 1, 0. Minus 1 minus 0, minus 1. So here are the vectors AB and AC, and then you do AB cross AC. If you get the vector 0, then you conclude. AB cross AC, we cover this, and you take that determinant 0. Then minus, you take this out, you get 1 plus 3, 4. So minus 4. It's not 0, so this is already not the vector 0. And then you cover this guy, you get 0. So this is not equal to the vector 0. And that means that A, B, C are not on the same line. Now, that being said, knowing that they are not on the same line, we know therefore they form a triangle. I can ask you, what is the area of the triangle ABC? Right? So the area, because triangle, it's 1/2 magnitude of AB is AC, which is 1/2 magnitude, and the cross product is, we just found it, 0, -4, 0. So that's 1/2 square root of 0 squared plus -4 squared plus 0 squared, which is 4/2 equals 2. So the area of that triangle is 2. Now we could ask another question, 3. Find the area of the parallelogram with sides AB and AC. So in that case, that area will just be equal to the magnitude of AB cross AC, which in this case is 4. Any questions? Now, when we have 4 points in the space are in the same plane or complanary, that'll be even only if say 4 points here, if we call them A, B, C, D. We have 4 points A, B, C, D in the space. They are in the same plane if and only if A, B cross AC, this would form a plane. A, B, C would form a plane if these things were in the same plane. And therefore, if the third one is still in the same space, then the dot product with AD will be equal to 0. Why is that? Because the cross product of AB and AC is both orthogonal to AB and AC. And if D is in the same plane, then this vector is orthogonal to AD as well. That's why if 4 points A, B, C, D are in the same plane, then AB cross AC dot AD is equal to 0. Okay. And when it's not equal to 0, the absolute value of this quantity is actually the volume. Let's see example. Take a point and do the work here. A with coordinates 2, 2, 2. B with coordinates 1, 1, 1. C with coordinates 1, 0, 1. And D with coordinates -1, 1, 0. And the question is, are these 4 points in the same plane? Want to try, Jason? Is he here?
Yeah, I'm here.
Want to give it a shot?
I forgot how to form the vector AB.
Sydney?
I'm honestly not really sure what to do from here. So
Form the vector AB, form the vector AC, form the vector AD, and compute the AB cross AC dot AD as done earlier. Gauge. Is Gauge here? Patient.
I can do it if you need somebody to.
Yeah.
I can do the problem if you need somebody to work it.
Let's go ahead.
So the first thing I did was find the vectors for AB and AC. So for the vector AB, I got the coordinates -1, -1, -1. And then for AC, I got the coordinates -1, -2, -1.
Mm-hmm.
And then I set up the cross product of AB and AC. And so
What is that?
for AD, I had -3, -1, -2.
All right, now you gotta get the cross product.
So for that one, I set up the first coordinate. I had the matrix -1, -1, -2, -1. And then the next one, negative, and then the matrix -1, -1, -1, -1. And for the next matrix, I had -1, -1, -1, -2.
Okay.
And then for doing all the determinants for it, I came out with the coordinates -1, 0, and then 1.
That's correct. And then AB cross AC dot AD, and that's -1, 0, 1 dot -3, -1, -2. What you get?
I got 3 plus 0 minus 2. So it came out to 1.
And that one is not equal to 0, so
So the points are not on the same plane.
Yep. That's it. Again, and I'll remind people that most of the time it's done here in class. You don't get it and you don't do the work, you prepare yourself for failure of the class. That's it for me today. Thank you.
Thank you, Dr. Longo.